The goal of step 26 is to figure out whether or not a relation is a function. And a relation is basically just a set of ordered pairs, or an infinite set of ordered pairs, like the graph of a line is a whole bunch of ordered pairs all connected together. Sometimes relations will be functions, but not all relations are functions. So first we start off with just a little bit of vocabulary here, things that you probably already know. You probably already know what an ordered pair is. We've been using them all year long. You probably know that the x-axis is the horizontal axis, also known as the x-axis, and our vertical axis is the y-axis. The origin is obviously right here at the center at the ordered pair 0, 0. Sometimes we represent our relations as mappings. That just means that we put the domain in one bubble and we put the range in the other bubble. The domain are all the x values, and the range are all the possible y values. And then you draw an arrow connecting them. So for instance, we have the ordered pair -2, 4. We have a -2 in the domain, and there's an arrow over to the 4. We have a -1, 4. So we start at -1 in the x domain and go over to 4 in the range. You don't need to repeat any of these values. You can just write them once and draw multiple arrows getting from one to the next. There are different ways to represent all of our relations. We can write them as ordered pairs, which again, we've been using ordered pairs all year, figuring out the slope between 2 points, graphing lines. You can make a t-table where the x's are on the left and the y values are on the right. You can actually make a graph where you plot the ordered pairs, or finally the mapping. Those are the 4 different ways to represent relations. When we're talking about relations, there are x values and y values. The x values are always going to be independent. These are going to be our x values. The y values are going to be dependent. And I'm going to give you a couple examples of how this works in real world problems. For example, the dance committee is selling tickets to the fall ball. The more tickets they sell, the greater amount of money they can spend for decorations. So we have two things that are varying: how much money they make and how many tickets they sell. One depends on the other. How much money they make depends on how many tickets they sell. So let's go ahead and type that in. It'll be faster than trying to write it. That is background. Okay. The amount of money depends on the number of tickets sold. You cannot do it in reverse. The number of tickets sold doesn't depend on how much money they make. It only works in the one direction. Same with the movies. The average price of going to the movies has steadily increased over time. So the average price depends on time. The average price depends on time. Let's add that in. For instance, you could say, well, I want to turn back the clock and make it 1945 again. Let's start charging 50 cents for a movie. That's not going to make time change. Okay? You cannot control time. Time is always independent. The amount that it costs to go to a movie depends on time. You cannot do it in reverse. You cannot say that time depends on the average price. All right. Let's look at these examples here. We have the air pressure inside the tire increases with the temperature. Well, let's think about this. When it gets really, really cold out, your tire pressure, like the air inside, kind of compresses a little bit, and your tires almost seem a little more flat. I don't know if anybody's ever witnessed that with their parents' vehicle. In the wintertime, you might get a low tire pressure sensor, where it's because all the air pressure in the car is so cold that it just condenses and your car thinks that you're getting a flat tire, when in fact you're not. And vice versa, in the summer, the air expands a lot. So one thing to consider is to think about this. Like right now, it's kind of chilly outside. And gee, I really, really wish it was like 90 degrees outside. If I go out now with an air pump and inflate my tires a whole bunch, will it make it hot outside? No, because the temperature doesn't depend on the tire pressure. But my tire pressure depends on the temperature. My tire pressure will change based on the temperature. Tire pressure, let me actually, just having a hard time fitting in what I'm trying to type here. Let me just zoom out. Tire pressure depends on the temp. So we would say that the tire pressure is dependent, the dependent variable, and the temperature is the independent. It's the one you can't control. Think about if someone has a very independent child. They're very difficult to control because they just know what they want and they just go for it. All right. As the amount of rain decreases, so does the water level of the river. So the water level of the river depends on the amount of rain. The amount of rain doesn't depend on the water level of the river. If they decided to come through and put a hose in the river and suddenly the water level's rising, it doesn't make it start raining outside. It doesn't control the other thing. The next example is to just talk about how we can represent real-world situations in a graph. So as you can see in this first graph here, we have distance, which is depending on time. Time is independent. Distance would be dependent. It depends on time. Because remember, we can't control time. So it looks like when time is 0, Francesca starts riding her bike and the distance is going up, so she's getting further away from home. And then the distance doesn't change for a set amount of time. And it's not labeled on the graph, but we could make it labeled. Maybe this is 1, 2, 3, 4, 5. Maybe we're talking minutes. So for the first minute, she's riding away from the house, wherever she started. And then from minute 1 to minute 3, she stopped. Maybe she stopped at a red light. Maybe she stopped to talk to a friend. Maybe she stopped to tie her shoe. But she stopped. Her distance does not increase. And then after the 3-minute mark, it continues to increase. So she's then getting further away from her original location. On 3A, we're looking about driving to school. Again, the person starts off driving, then they stop. Maybe it's a red light, maybe it's something else, maybe it's traffic. Then they start going a little bit. But one thing we can tell from here and here, from these two pieces, in fact, I'm going to make them different colors. This original gold piece versus this pink piece right here. Which piece were they going faster, do you think? Anyone can share an answer right now. What do you think? Yes, the first one, they were going faster. We know they were going faster right here because it has a steeper slope. Compared with the pink, they were still moving away, but at a slower rate because that has a smaller slope is what I'm trying to say. And then these two green pieces here, they weren't moving at all. because the slope is 0. And then finally, the slope is going up again, so the person driving to school is now getting further away from home. In this next example, we're looking at someone's income versus time. So it looks like this person started out making money. They kept getting a raise, and then they got a big raise right here. In fact, let me erase that again. So they were working, they were increasing in money, and then it spikes up, and then they continue to keep getting a raise each year. And then for a few years, they didn't get a raise because the slope is 0 there. And then again, from that point forward, they were continually getting a raise each year. So that's how you can interpret those graphs from real-world examples. Finally, how can we tell if a relation is actually indeed a function? Well, an example that Mrs. Keith actually used a few years ago that I really like is if you think about a vending machine. A vending machine has different buttons on it usually, like buttons 1 through 8. And if you push 1, you get Cheetos. And if you push 2, you get Doritos. And if you push 3, maybe you get Skittles. Well, it functions if every button gives you a different product. If you pushed 1 and sometimes it gave you Cheetos and sometimes it gave you Doritos, you would say this machine is not functioning properly. This is not right because they cannot share X's. That's how you can tell. So right here, looking at this first mapping, none of them share X's. Every single X goes to a different range. Every single range has a different X. Let me show you what I could do with my arrows to break it. Right now it's a function. But if I do this, now I have a repeated X. When I push -3, I don't know if I'm going to go to 5 or if I'm going to go to 2. That would not be a function. But as long as we have X's with just one arrow coming out of them, it is a function. All X values have only one arrow. Now, personally, that tends to take a little bit of time because if your arrow looks like this, that is a function. Oops, nope, I lied. Let me give you another example. I forgot I have to add a number here to make this happen. If I do this, if I put 5 on our list and make him go to number 1, that is a function because number 5 only has one arrow. It's okay to repeat the Y's, but it's not okay to repeat the X's. And I find that to be a little bit confusing sometimes when I'm thinking about it. It's hard to remember which one can repeat and which one can't. So an easier way to think about it is to think about the vertical line test. If you can pass a vertical line over the graph, and I'm going to actually use a ruler to represent my vertical line. If I can pass this vertical line across the graph and only hit the graph at one point, I have a function. So this is an example of a function. Let me give you an example of something that would not be a function. If I draw something that looks like this. Now when I try to pass my graph, do you see how it hits the graph at 2 locations? It hits it here and here. That means it's not a function. It's a relation, but it is not a function. So this is not a function. On the flip side, this blue one is a function. And you can do this same idea, the same concept by plotting these points on a graph. So let's Let's just do this with a simple sketch, actually. Because again, sometimes looking at, oops, I moved my picture here. Make it a background image. There we go. When you're looking just at an example with a mapping, it can be really hard to tell. So instead, if you just make a quick graph of it, -3, 1, 2, 3, up 5, 0, 3, 2, 2, 4, -1. You can see that if I were to pass a ruler, I would never be able to hit 2 points at the same time if I pass a vertical ruler. So if it passes the vertical line test, we consider it a function. So on the first one here, ignoring the explanation that's written on your notes, if we just look at this and quickly sketch these ordered pairs, -2, -3, doesn't have to be perfect, we're just getting a sketch, 0, 6, 3, 6, and 4, 9. You can see that those blue dots never land one right on top of the other, and they pass the vertical line test. So we would say, yes, that is a function. Again, just making a graph for part B, we would graph 1, 4, 3, 2, 5, 4. So far things are looking good. And then we have 1, -4. And that's where the problem occurs, because this fails the vertical line test. We cannot have an x value that has 2 different y values. So for this one, we say not a function. How about this next one? Let's take a vote. My friends in the classroom, do you think it's a function? Thumbs up, or not a function? Thumbs down. What's your idea on this one? If you need to make a sketch real quick to plot those points, you can do just that. 2, 1, 3, -2, and so on. How many say it's a function? How many say not a function? All right, let's see. Mostly thumbs down, that's right. It's not a function because 2 doesn't know if it should go to 1 or if it should go to -2. It fails the vertical line test right here. I have 2 points right on top of one another. Therefore, it fails, and we say this is not a function. You don't have to plot all the points to decide. As long as you can see that 2 of the x's repeat, it will not be a function. Okay, this talks a little bit more about the vertical line test in your notes there. Here we have a equation, and they're asking us, is this a function? Well, again, it's pretty straightforward and easy to tell if it's a function by just graphing it. And then when we pass our vertical line test over it, I'm going to grab my ruler. Here's my ruler. As I pass my ruler across the graph, it never hits the blue graph more than once at a time. So it is considered to be a function. And you could do the same with either of these, 3a or 3b, by graphing them as well. The last thing is to just talk about function notation. And you've actually been exposed to this a little bit already this year throughout our year.